So in this video, I'll look at the essential skills and techniques required to analyze cross-section data using regression analysis. So I'm going to, first of all, of course, import my data set here. This is a data set taken from the book by Green on econometric methods, a well-known textbook. It's the example that's in the chapter on heteroscedasticity. So reading the data in, have a look at the structure of it. We can see there's 100 observations on 7 variables. You've got some numeric variables and you've got some dummy variables. A quick summary gives us some descriptive statistics. Now, in fact, what the regression we're going to run, which Green runs, is where average expenditure is the dependent variable. So he first of all excludes those cases where average expenditure is 0, because that really wouldn't make much sense. So using the subset function here to only include where average expenditure is not equal to 0, that will return another data set, a subset. And if we look at that now, you can see we've only got 72 observations now. So 28 were removed. Now the model to estimate is here. So this is how you specify a regression model. You put the name of the dependent variable, a tilde, and then the independent variables separated by plus signs. So we've got age, own rent, income, and notice we're also including income squared here. So notice the power operator there, the little inverted V, and notice how you have to put this in. You can't just put income squared; it won't work. You have to put it inside inside this little function here, I. So I, and then in brackets income squared. So that's how you'd put in things like income squared or 1 over income or something like that. Now, that's how you set up the model, which I'm then storing in a variable. So let me enter that. And then to estimate the equation, you use the LM function, which is the standard function in R for linear regression. And you first of all put the variable containing the model. You could put the model in directly in there instead of mod1, but I prefer to set it up first and store it in a variable. And then you simply put data equals and the data frame, data 1. Then you store the results in a variable, and then you simply run the summary function on that variable, and there are the results. Standard printout, coefficient estimate, standard error, t-values, p-values, residual standard error, R squared, adjusted R squared, F statistics, and so on. Now, if you want to retrieve any of the values, like the fitted values or the residuals, you can easily do that. You simply use the various functions which are available. First of all, fitted, which will return the fitted values. So I'm putting fitted on reg1 and storing those in a variable pred1. Then I'm going to retrieve the residuals using the residuals function and store those. And now that I've done that, I can then plot these things. So a simple plot of the residuals, just use the plot command on the residuals variable that you've just created. And we get a straightforward plot of the residuals. Of course, you could add a title to this and maybe a better y-axis label and so on. We've seen how to do that in the previous video that I did. Now, another thing you might want to do is run a scatter graph of, say, for example, the residuals against predicted values. That's often gives an indication of potential heteroscedasticity. Now, to do that, again, plot, and then you put the dependent, the variable on the vertical axis, res1, tilde, and then the variable on the horizontal axis. And that will give me a simple scatter graph of the two, like that. And again, you could add options here to create a title and a better Y label. You could put main equals for the title, Y lab for the Y-axis label, X lab. I looked at those options in the previous video. Okay, now here we've got are results showing the t values, which of course are test each coefficient value individually for significance. What you often want to do, of course, is do a joint test of significance. So, for example, looking at these two variables here, the coefficient values on income and income squared both appear to be individually significant. Are they jointly significant? Well, for that, of course, we can run an f-test or a chi-squared test. Now you do that by, first of all, getting the results of the restricted model. In this case, I'm going to assume that the two coefficients on income and income squared are 0, so the restricted model would exclude these two variables. And now you could do that by setting up the model here without these variables and then estimating it. A slightly quicker way is to use the update function. So you simply put update, then the variable containing the results of your unrestricted model, then you have this option here, formula, and it's formula dot equals, then you put dot tilde dot, which simply means use the same dependent variable and the same independent variables, but minus these two. So you can see how you put that. So dot tilde dot minus income squared. So that's going to exclude those two. And the results get stored. And if you do the summary on that, you'll see exactly that's what we get. So we've estimated the model now excluding those two variables. We can now do an ANOVA and f-test on those to test that joint restriction. So the function is ANOVA, and then you simply put the name of the variable containing the restricted model results, comma, unrestricted. I don't think it actually matters which way around you put them, but I tend to put the restricted first. And that gives me a simple f-test of that restriction. Now that, of course, is a small sample test. If you wanted a large sample test, a chi-squared test, you can do that using the WALD-test function, which is available in the LM-test package. This package, LM-test, is extremely useful. In fact, it's essential for doing regression work because it contains all the standard diagnostic and specification tests. So make sure you install this package and then we load it, of course, using the library function. So let me load LM-test into memory, and then these various functions, these diagnostic tests and so on will be available. So we can now run WALD-test, which is in the LM-test package. Again, the syntax is the same as ANOVA. You put the restricted model, the unrestricted. Now, if you leave it at that, as I did here, you'll get the same f-test as we've already got. So in order to get the chi-squared test, you put test equals chi-squared. And that will give me a chi-squared test, a large sample test of that restriction. Now, of course, these tests, these specification tests, the t-test, the f-test, and so on, are only valid if you have no problem with your residuals, no heteroscedasticity, no autocorrelation, and so on, if the classical assumptions are satisfied. What you would actually probably want to do before you run these tests, of course, is to do some tests. Now, typically with cross-section data, you often, not always, but often have a problem with heteroscedasticity, and that is indeed the case with this data set, and that's why it's being used in the chapter on heteroscedasticity in green. Now, we've already seen that if you look at the plots that we ran here, particularly the residuals against predicted, that is suggestive of heteroscedasticity. If you also have an idea of which variable might be causing the non-constant variance, then you can look at that graphically. And Green notes that often with data on expenditure by income, then the variance of expenditure for households, individuals on higher incomes is wider than for lower incomes, because having a higher income gives them more scope to vary their expenditure. So it's likely here, it's possible that the heteroscedasticity is related to the income variable. Now, we can check for that, firstly by running creating a little scatter graph of residuals against the income variable, like this. As you can see, it's very suggestive of heteroscedasticity, a wider variance being here at higher income levels. But of course, that's only suggestive. We can run some standard statistical tests. Now, there are a number of tests for heteroscedasticity. All of them, or certainly most of them, are available in the LM test package. One, for example, is the Goldfeld quant test. You can run that using the GQ test function here in LM test. So it's GQ test, and then the arguments are firstly the variable containing your results, of course, reg1. You then use the order.by argument to tell it which variable to order by, in this case income. Notice you put tilde income, and then tell it the data set. And that gives you a Goldfield want test. But probably the most commonly used, the most useful test of heteroscedasticity is the Broich-Pagan test. And again, that's available in LM tests. It's the function BP test. Now, if you want information, of course, on this particular function, then, of course, you can look at the help system. All you need to do, of course, is to place your cursor on the appropriate function and press the F1 function key, which brings up the help system for that particular function. So here's the help for Broich-Pagan test. It tells you the syntax here, the various arguments that you can use. And of course, most of them will have default values. And it's always very useful to look at the help system. So we can easily run that by simply putting BP test, then the variable containing your results. And then if you want the straightforward test where it will use all the independent variables as what's called the variance function, then that's all you do. You put BP test, then the name of the variable containing your results from up here, and then again specify the data. You'll see that if you look in the help system here, then you'll see it says that for the variance formula, by default, the same explanatory variables are taken as in the main regression model. So if you don't specify that, it will use all the ones here. So that can be run. Now, in fact, what it gives you by default is what's called the studentized Broich-Pagan test, also known as the Kronecker test, which is regarded as the better one, because the original Broich-Pagan test is sensitive to normality or non-normality in the residuals. I'll show in a moment how you can run the original one. Now, if of course you know which variable you think is to which the heteroscedasticity is related, then you can specify that in this var formula argument here. So same thing again, but this time we specify this variance formula to be, and again you put tilde and then the variables you want to include. So I'm including income and income squared here, which is what Green does in his text. And also I'm using the studentize equals false argument here so that we get the original Broich-Pagan test rather than the studentize one. So that gives me that test. And then finally I've run the same test here, but without the studentize equals false option, so I'll get the original test like that. So as you can see, you can run a Broich-Pagan test very, very easily here using the function in the lmtest package. Now, as I've just said, the difference between the studentized and the non-studentized is that the normal one, the original one, is sensitive to non-normality in the residuals, and Green points out that the big difference here between the non-studentized, the original one, and the studentized one is suggestive of non-normality. Now, a standard test for normality residuals, of course, is the Jacques-Berer test. Now, you can run that here if you load up the T-series package, because that's where the Jacques-Berer test is. So again, if you haven't got that package, install it, and then let's load it into memory, and then I can run the Jacques-Berer test on the, notice you run it on the residuals, so that's another reason why I wanted to store those residuals in a separate variable. And we get that value, which does indicate non-normality. So there's certainly indication of heteroscedasticity here. How do you deal with that? Well, there are a number of ways, but a common way these days is to re-estimate the standard errors, allowing for the heteroscedasticity. These are known as robust or heteroscedasticity consistent standard errors. Here were the original ones here, and of course that then gives you particular t-values. These will be incorrect if you've got heteroscedasticity, so you can, there are these various alternative estimators which allow for it, which are robust, which are heteroscedasticity consistent. Those are all available in the sandwich package. So again, install that and then load it up. And then you can simply re-estimate your coefficient values here and standard errors and so on. In other words, you can get this table here again, allowing for heteroscedasticity. Now, there are various types of this, which of heteroscedasticity consistent, it's difficult to say, standard errors. There's the original white ones, and then there's other ones. These in R go under the names HC0, HC1, HC2, and so on. So you can get all of these by using this coef_test function. Now, what I've done here is I've first of all brought up the original ones so that I can compare them. So first of all, I'm going to run coef_test simply on reg 1, and that will bring up the original ones. As you can see, if we just look back and compare, these are the ones from our original estimation. There we are. I've done that so that when I do the heteroscedastic ones, I can easily compare them because they'll be one on top of each other. So to get to re-estimate these, the estimates, of course, are the same, but the standard errors and t-values and p-values would be different. You simply put this additional argument here, vcov dot equals, and then you specify this vcov hc argument. If you do that, it will give you by default the HC3 estimator. If you then want a different one, HC0, HC1, as you can see, what you put is this additional argument here, type. So you put type equals HD0, or type equals HC1, type equals HC2, and so on. So here we can get the HC0. And as you can see, how the standard errors are changing here. The coefficients, of course, don't change. They're still consistent and unbiased, I believe, but the standard errors are changing, and hence so are the t-values. It doesn't seem to be making too much difference to the individual significance. Let's try HC1 finally. There we go again. Different standard errors, not radically different. And then finally, since these standard errors, these original ones, don't appear to be accurate, then that means, of course, that our f-test up here and our wall test wouldn't be correct. So you can re-estimate that, redo that test, allowing for these different, for the heteroscedasticity. In other words, you can redo it using the robust standard errors. And you simply do that again with the Walsh test function. So again, it's the same syntax as we had up here, restricted model, unrestricted, but now you add this and test equals chi-square, but now you add this additional argument here, vcov equals vcov hc, and then in brackets reg1, and then the type option. So that will rerun the chi-square test here, but using these robust errors. And there we get that. So that shows you quickly how to use R to run some standard regression analysis on some cross-section data.